In the most terrifying scenario for a modern metropolis, the skyscraper might not be the first thing to fail. There is no shattered glass raining down from the clouds. There are no snapped concrete pillars or collapsing steel frames. The grand facade of the city remains entirely intact against the sky. Instead, the failure begins quietly, right beneath the surface of the streets. The ground itself, the very foundation that feels absolute and permanent, suddenly loses its ability to carry the weight of everything built above it. A small fissure appears on the pristine asphalt of a luxury boulevard. Then, a mixture of dark water and sand begins to bubble up from the crack, spilling over the meticulously manicured sidewalks. The pavement slowly buckles, warping the geometry of the street. Behind this surreal deformation, the record-breaking towers stand completely motionless, seemingly victorious against the tremor. But this is an illusion of safety. The true catastrophe in a highly engineered urban center does not require a building to fall. It only requires the hidden arteries connecting that building to the world to sever. This brings us to a crucial question about one of the most ambitious real estate and tourism markets on the planet. How could a devastating infrastructure failure happen in Dubai, a city that does not sit directly on a major active seismic fault line? The answer lies hidden in the microscopic spaces between millions of grains of sand, waiting for a very specific, low-probability, high-consequence trigger. If you are watching this, you already know that the official brochures only tell part of the story. Subscribe to the channel and join us as we investigate the hidden vulnerabilities beneath the world's most glamorous skyline. Because the first sign of a systemic crisis rarely comes from the top of the tower. When people think of the hidden costs behind Dubai, they usually point to economic vulnerability, real estate oversupply, or the immense environmental pressure of maintaining a luxury oasis. Critics frequently discuss the heavy reliance on international aviation, the shifting trends in global tourism, or regional instability. But there is a physical vulnerability built into the very geography of the coastal expansion, one that connects global economics directly to geotechnical reality. A natural counter-argument immediately arises. Dubai is not Tokyo, San Francisco, or Istanbul. It is not famous for earthquakes. This is a mathematically true statement that often creates a false sense of absolute security. The danger here does not come from a massive fault line tearing through the center of the financial district. The threat we must investigate is the combination of distant seismic sources and the highly specific, incredibly sensitive local soil conditions. Earthquakes are merely the initial trigger. The soil decides what happens next. To understand the true nature of this hazard, we must look away from the gleaming skyline and cast our view across the regional map. More than 100 kilometers away lies the Makran subduction zone, a massive tectonic boundary where the Arabian plate is being pushed beneath the Eurasian plate. Historically, this zone has produced massive seismic events. When a large earthquake occurs there, it releases tremendous amounts of kinetic energy that travel through the earth crust in the form of seismic waves. High-frequency waves tend to lose their destructive power over long distances. But low-frequency waves behave differently. They can travel hundreds of kilometers with remarkable efficiency. When these long-period waves reach the coast of the Arabian Peninsula, they encounter deep layers of soft sediments and reclaimed coastal soils. Instead of dampening the energy, these specific soil types can actually amplify the shaking. This means a distant earthquake can create prolonged, rolling tremors right under the most valuable tourism and residential real estate in the world. But distant tremors alone are not enough to bring a sophisticated urban network to its knees. There is a missing component, a hidden mechanism waiting in the dark. That mechanism requires 3 specific conditions to meet at exactly the wrong time. To understand the hidden fault line beneath the luxury economy, we must zoom in past the regional map, past the city grid, all the way down to a single grain of sand. The phenomenon that engineers fear in this specific scenario is called soil liquefaction. Despite the cinematic-sounding name, the soil does not literally melt or turn into a river of water. The reality of liquefaction is a mechanical failure of granular structure, and it is far more insidious. The first condition required to trigger this trap is the presence of loose, granular soil, specifically sands and silts, that have a structure capable of being rearranged. The second condition is saturation. The spaces between these individual grains of soil must be entirely filled with water, which is common in areas with a high groundwater table or reclaimed coastal land. Under normal, everyday conditions, the weight of the city is supported by the physical contact between the solid grains of sand. The building pushes down, the grains push against each other, and the load is safely transferred deep into the earth. The water resting in the microscopic voids between the sand grains carries very little of this immense pressure. But when the third condition arrives, everything changes. A sustained seismic tremor introduces rapid, cyclic vibration into this delicate underground matrix. The vibration forces the loose grains of sand to shift, trying to consolidate and pack themselves more tightly together. As the sand grains attempt to compress, they squeeze the water trapped in the microscopic spaces. Because the shaking happens so incredibly fast, the water simply has no time to escape or drain away. With nowhere to go, the water pressure inside the soil spikes dramatically. This is known in geotechnical engineering as elevated pore water pressure. Within seconds, the water pressure becomes so intense that it pushes the sand grains apart, breaking the physical contact between them. The soil abruptly loses its shear strength, and its effective stress drops to zero. In an instant, a solid foundation capable of supporting heavy machinery behaves like a viscous liquid. The ground has not melted, but it has completely lost its ability to hold up the world above it. You might worry about a visible crack in a load-bearing wall, but the truly terrifying process is the one happening in the dark, silent layers of earth that you can never see. This geotechnical reality forces us to look closely at the geographical layout of Dubai tourism and economic engine. The city has achieved unprecedented global fame by expanding its footprint aggressively into the sea. The iconic artificial islands, the sprawling luxury beachfront resorts, and the dense marinas are marvels of human ambition. They form the absolute core of the regional tourism brand. However, these exact environments often share the specific characteristics required for liquefaction susceptibility. They feature engineered sand fills, proximity to the ocean, and a naturally high groundwater table. It is crucial to clarify that we cannot treat the entire city as one uniform geological block. You cannot drill a single borehole and extrapolate the results to condemn the entire coastline. Liquefaction susceptibility is highly localized, meaning two plots of land, just a few streets apart, can react completely differently to the exact same seismic wave. But the sheer concentration of high-value assets situated in these potentially sensitive coastal zones creates a unique exposure profile. Exposure is a critical concept here. Hazard is the probability of the earthquake happening. Susceptibility is whether the dirt can turn to liquid. Risk is what happens to the people, the billions of dollars of investments, and the continuous flow of global tourists when the hazard meets the susceptibility. The risk is magnified because the economic model relies heavily on the perpetual, flawless operation of these ultra-luxury spaces. A five-star resort charging premium rates cannot function if its immediate surroundings are compromised. The tourism pressure is already immense, with fierce regional competition and fluctuating global economic conditions. Any physical disruption to this meticulously crafted image carries an enormous financial penalty. If the underlying soil possesses this hidden vulnerability, the obvious question is how engineers have allowed these massive structures to be built at all. If the ground can fail, why do the towers keep rising? The answer lies in the invisible, highly sophisticated defense systems buried deep underground. The narrative of a vulnerable city often ignores the extraordinary engineering competence that actually built it. This is not a metropolis constructed blindly on shifting sands by developers who ignored basic science. Dubai possesses rigorous building codes, stringent seismic design regulations, and a municipality that mandates comprehensive geotechnical investigations. Before a single drop of concrete is poured for a modern high-rise, the ground is thoroughly interrogated. Engineers conduct deep exploratory drilling, standard penetration tests, and cone penetration tests to map the exact stratigraphy of the Earth. They measure the groundwater levels, analyze the particle size distribution, and calculate the exact density of the granular layers. When they identify a layer of soil susceptible to liquefaction, they do not simply hope for the best. They deploy massive ground improvement techniques, using heavy machinery to compact the loose sand, or they replace the problematic soil entirely. More importantly, they bypass the vulnerable layers altogether by driving massive steel and concrete piles deep into the earth. These foundation systems reach down dozens of meters, anchoring the incredible weight of the skyscraper into denser, highly stable geological formations below. The structural frames of these towers are meticulously designed to absorb lateral seismic forces, allowing the buildings to flex and sway without catastrophic failure. The engineering shield is incredibly robust. A modern tower built to these rigorous codes is designed to survive the shaking, protecting the lives of everyone inside. This is the moment where an investor, a resident, or a tourist might breathe a sigh of relief. The towers are safe. The foundations are deep. The catastrophe is averted. But survival does not mean the crisis is over. Survival is merely the baseline requirement for human safety. In a complex urban ecosystem, surviving an event and continuing to operate are two vastly different things. And this is where the grand illusion of total security begins to fracture. Let us introduce the great reversal of the engineered city. What happens if the brilliant, multi-million-dollar foundation system works perfectly, but the city around it does not? The deep piles hold the massive skyscraper exactly where it is supposed to be. The tower stands tall, rigid, and victorious. But the untreated, susceptible soil surrounding the perimeter of the building experiences liquefaction and begins to settle. This creates a devastating phenomenon known as differential settlement. The ground literally drops away from the static, immovable structure. The gap between the building and the surrounding earth might only be a few dozen centimeters, but in an interconnected urban grid, a few centimeters is a death sentence for infrastructure. The failure points multiply instantly. First, the rigid pipes connecting the building to the municipal water supply are subjected to immense shearing forces as the ground sinks. They snap. Next, the heavy sewage lines lose their gradient or simply break apart, spilling waste into the subsiding soil. The massive underground electrical conduits, which power the elevators, the lighting, and the crucial communication networks, are stretched beyond their tensile limits and sever. The meticulously paved access roads and grand driveways warp, crack, and separate from the entrance ramps of the underground parking garages. The pedestrian bridges and elevated walkways that connect luxury malls to transit stations experience severe differential displacement, rendering them structurally unsafe to cross. The building itself has not suffered a single cracked window. Its concrete core is perfectly intact, but it has been forcibly amputated from the life support systems of the city. The most expensive, highly protected asset in the district has suddenly been transformed into a dark, isolated island of concrete and glass. The realization sets in that the true fragility of a modern luxury destination is not the skyscraper. It is the invisible, sprawling, fragile web of utility connections that makes life inside the skyscraper possible. To grasp the full magnitude of this infrastructure cascade, we must watch the disaster unfold on a timeline of minutes and hours. In the first 15 seconds of the tremor, sensors across the city record the abnormal low-frequency acceleration. Automated safety systems instantly command hundreds of high-speed elevators to stop at the nearest floors and open their doors. Most residents and tourists feel a disconcerting sway, but panic has not yet set in. Between 15 and 45 seconds, the vibration continues. In specific coastal zones with loose, saturated fills, the pore water pressure hits its critical threshold. The invisible mechanical failure occurs. Sand boils erupt on immaculate golf courses and luxury promenades, pushing dark sludge onto the grass. The ground subsides unevenly. By the 10-minute mark, the cascading consequences paralyze the grid. Building management systems trigger cascade alarms as municipal water pressure drops to zero. District cooling systems, which are the absolute lifeblood of survival in a desert metropolis, automatically shut down as their massive chilled water pipelines warp and lose integrity. Emergency generators might kick in, but their fuel reserves are finite, and the roads required for refueling trucks are now fractured and impassable. Several hours later, structural engineers face an agonizing reality. They can quickly determine that the main towers are structurally sound and safe from collapse, but they cannot restore the severed utility connections buried under deformed earth. Without district cooling, without running water, and without safe fire suppression systems, the authorities have no choice. They must order the evacuation of completely undamaged buildings. Tens of thousands of tourists, expatriate workers, and residents are forced onto the streets of a city that has suddenly lost its ability to regulate its own environment. The disaster is not characterized by falling debris. It is characterized by suffocating heat, darkness, and logistical paralysis. The most terrifying phase begins when the shaking stops, and the engineers must figure out how to restart a deeply interconnected machine that has broken into 1,000 disconnected pieces. The transition from a localized physical disruption to a massive economic crisis happens almost immediately. This is where the geopolitical reality, the tourism pressure, and the economic vulnerability of Dubai violently intersect with the geotechnical risk. The city economic model is heavily predicated on the perception of absolute, uninterrupted perfection. It is a premium destination that charges premium prices for a seamless, frictionless experience. When a sprawling luxury hotel is forced to evacuate its guests, not because the roof caved in, but because the toilets will not flush and the air conditioning is dead, the reputational damage is instantaneous. In the age of social media, images of stranded tourists sitting outside pristine, dark hotels spread globally in minutes. The immediate financial impact is staggering. Hotels must refund bookings, cancel massive corporate conferences, and pause their lucrative food and beverage operations. The revenue per available room, or RevPAR, which is a critical metric for the hospitality industry, plummets towards zero in the affected districts. But the bleeding does not stop at the hotel lobby. The massive retail sectors, the luxury malls, and the high-end dining establishments depend entirely on the foot traffic generated by those tourists. When the tourists are evacuated, the retail ecosystem starves. Aviation, which is the beating heart of the Dubai economy, faces a bizarre paradox. The international airport might remain completely functional, its runways perfectly intact. But if the city cannot accommodate the influx of visitors due to infrastructure failure in key districts, airlines must inevitably cancel flights or reroute passengers. The connecting traffic might continue, but the highly profitable point-to-point tourism stops. This exposes a severe hidden cost within the economic system. The cost of recovering from liquefaction-induced infrastructure failure is astronomical. Digging up deformed roads, replacing shattered district cooling pipes, and re-leveling sunken utility grids requires billions of dollars and months of disruptive heavy construction. During this prolonged recovery period, the affected districts become active construction zones, further destroying their appeal to high-paying international travelers. The real estate market, already sensitive to oversupply and regional competition, faces a crisis of confidence. Investors realize that owning a structurally sound apartment is meaningless if the neighborhood around it cannot be guaranteed basic municipal services. Property values in susceptible zones can stagnate or drop, even if the buildings are flawless. This is the ultimate paradox of the luxury urban exposé. The city is built to project endless growth and defeat natural limits, yet it remains hostage to the mundane, invisible utility pipes buried in the sand. Before we allow this scenario to paint a picture of inevitable doom, we must apply scientific skepticism to the panic. The existence of a risk does not mean a disaster is mathematically guaranteed to happen tomorrow. There are 6 crucial variables that dictate whether this nightmare scenario actually materializes. First, the intensity and duration of the seismic shaking must be sufficient to trigger the pressure spike. Second, the distance and pathway of the seismic waves from the epicenter matter immensely. Third is the specific type, density, and particle distribution of the soil at a given location. Fourth is the exact depth of the groundwater table on that specific day. Fifth is the thickness and confinement of the susceptible soil layer, and sixth is the resilience, flexibility, and engineering of the connecting infrastructure itself. There is no single, terrifying number that can declare the entire city either completely safe or completely doomed. 2 adjacent plots of land, developed by 2 different companies with different engineering budgets, will react entirely differently. The risk is not defined by sensational headlines predicting that the city will sink into the sea. The risk is defined by localized, highly specific geotechnical data. To combat this, Modern urban planning introduces layers of defense beyond just deep foundations. Forward-thinking engineers now utilize flexible utility joints designed to accommodate significant ground movement without snapping. They build redundant networks, ensuring that if one main water line fails, another can instantly take over the load. They implement advanced dewatering techniques and deep soil mixing to permanently alter the characteristics of the ground before the first brick is laid. Engineering cannot prevent an earthquake, nor can it completely eliminate the laws of physics that govern saturated sand. But highly funded, rigorously applied engineering can prevent a minute of shaking from becoming 6 months of economic paralysis. The question is not whether the city possesses the technology to protect itself. The question is whether that expensive, invisible technology has been applied uniformly across every single kilometer of the sprawling, rapidly constructed coastal expansion. Dubai has built one of the most ambitious, visually stunning skylines in human history by constantly declaring victory over the harsh limits of the natural world. It has conquered the extreme heat, tamed the arid desert, and literally redrawn the coastline to accommodate its relentless economic drive. But every tower, no matter how tall, how luxurious, or how technologically advanced, must eventually transfer its massive weight to the earth. The physical foundation of the city is inextricably linked to its economic foundation. In the event of a rare but highly impactful seismic tremor, the ultimate test of the city will not be measured by the strength of its concrete cores or the flexibility of its steel frames. The test will be measured by the resilience of the invisible systems buried in the vulnerable sand. The most terrifying revelation is that a city does not need to lose its skyline to suffer a catastrophic systemic failure. It only needs to lose the hidden connections that make the skyline habitable. A standing tower in a paralyzed district is a monument to a broken system. This video is an analytical documentary based on publicly available data, geotechnical principles, and urban economic theory as of the time of research. The analysis explores systemic vulnerabilities, infrastructure dependencies, and hypothetical risk scenarios. It does not predict specific future disasters and is not intended to attack any residents, demographics, or organizations. Conditions regarding tourism, real estate, and structural engineering are subject to change. This content is for educational and investigative purposes only and does not constitute financial, investment, or personal travel advice. If you value documentaries that look beyond the skyline and investigate the hidden mechanisms of our modern world, make sure to subscribe. The next warning sign is rarely where the official brochure tells you to look.